Here are some solutions to the worksheet problems from really this is from section 6.4. I'm not going to do the ones in number 1 because the same concepts are in number 2, where we have to actually solve the equation instead of just rewriting it. So just in interest of time, let's focus on these. So for a couple of these, there's more than one way to do it, because if in the equation we end up with exponential or logarithmic expressions on both sides of the equal sign that have the same base, then we can take advantage of the fact that these functions are one-to-one, and it simplifies the problem quite a bit. So let me just do a couple of examples of that, and then I'll show you that if you don't notice that it's not a big deal, because the more general method will still work whether or not you notice that. So for example, in part B, this is a good example of. Notice that 2, 4, and 8 are all powers of 2, and so that we can take advantage of that by rewriting the equation so that everything is written in terms of powers of 2. And so this problem emphasizes why our rules of exponents are useful, because on the left-hand side of this equation, this first part is really just 2 to the 2x, right? When we have a power to a power, those powers get multiplied. So this is 2 to the 2x, and this is 2 to the x squared. And so when we multiply 2 powers of 2, the exponents will get added. So on the left-hand side, the rules of exponents tell me that the left-hand side can be rewritten as 2 to the x squared plus 2x. And of course, the right side is 2 to the third. And so because the 2 to the x function is 1-to-1, it means that there's no way that you could have two outputs of the 2 to the x function that would be equal without the inputs being equal. And so this means that the two inputs into the formula, so this is one input into the exponential formula, this is the other side, those inputs have to be equal. So I'm not canceling the 2's or anything, I'm just saying that the only way for powers of 2 to be equal is if the powers are equal. This should be a 3. And now this is a normal quadratic polynomial problem, and so I would rewrite this so that 0 is on one side, and this only takes a second to realize this factors. And so my solution set is x could be -3 or x could be 1. So that's the answer to B. And so that takes advantage of the fact that the exponential function base 2 is 1-to-1, meaning that if you have two outputs that are equal, then the inputs for those two things have to be equal. In other words, it's impossible to get the same output from two different inputs in an exponential function. All right, same thing happens with the logarithmic function, and so in this problem E, the same thing's going to happen. There's no way that you could have the log, doesn't matter what base, but there's no way you could have the log of two different inputs giving you the same output. And so therefore, if the output of the log using input 2x plus 3 is equal to the output of the log when the input is 5x minus 7, then it must follow that the inputs 2x plus 3 and 5x minus 7 are equal. So notice it only works because we have the same log function here, log base 2, log base 2. 2 to the power, 2 to the power, right? So it's not just some random way you just could ignore the logs of the exponentials. It's a very rare kind of problem that happens on. And that's why I wanted to show you that first. So in this case, if we solve this the rest of the way, what is x, like 10/3 or something? Yeah, I think x is 10/3. Anyway, you can check, but that's just linear, so that's not hard to solve. So. Okay, so the more general solution method we talked about in class, and that is first isolate the exponential or log that's got your x stuck in it. So in this case, here's where my x is stuck. It's stuck in the exponent of this e to the x expression. So I want to isolate that first, which means divide both sides by 4, and now the e to the x part is by itself, and then we transform that into a log equation with the same base, and I always do this where I'll put my parentheses in my equal sign so I can really think about input and output. And I'll say the output of the exponential should become the input of the log, and the input of the exponential becomes the output of the log. So what happens when we change from the exponential form to the logarithmic form is that the inputs and outputs switch. Now, if you remember that, so that's a perfectly good answer as far as doing that on your calculator to get the 3 decimal place answer. Don't forget that log base e, this guy, log base e is also the same as ln. So if you calculate ln of 13/4, you'll get the, that's a good answer. This was fine as an answer, but if you have an ln button on your calculator, so you can calculate ln of 13/4 to 3 decimal places. Okay, and so so notice that makes problems easier. So for example, D, if I have to isolate the exponential part first, my x is here, so it's stuck inside of this 3 to the power, and so I'm going to subtract 5 from both sides and then divide both sides by 2, and I'll rewrite this equation as 3 to the 4x equals 1/2. That turns into a log base 3 equation, but instead of the input into the exponential being 4x, that's going to be the output, and instead of the 1/2 being the output of the exponential, 1/2 is going to be the input into the logarithm. And notice in this case that I'm not quite done yet because I still don't have x equals anything. So if I multiply both sides by 1/4, I'll have 1/4 log base 3 of 1/2 equals x. And so that would be my exact answer. A really important formula if you want to evaluate logs numerically to get a few decimal places of them. Again, you only have 2 log buttons on your calculator. You have one called log, which is code for log base 10, and you have one called ln, which is code for log base e, but you don't have a log base 3 button on your calculator, or at least most of you don't. And so this can be evaluated. We can get the approximate answer to this by using the change of base formula. So the 1/4, of course, is just 1/4, but this log part, we can evaluate that in our calculator by just doing ln of 1/2 over ln of 3. In other words, it's the log of the argument, it's the log of this input divided by the log of this base. And you can use your ln button or your log button, just make sure you use the same one twice, and that will be, that is equivalent to log base 3. So if in part A, for example, oops, let me just get rid of that, it's not going to scroll for me. So in part A, for example, if you didn't notice that everything in part A involved powers of 3, which they do, and so you can do number 3 just like you did, you can do letter A the same way you did letter B if you see all those powers of 3. But if you didn't notice that, then we can go through this process of say, well, let's isolate the 9 to the x part by first dividing both sides by 3. Let's change to the log form. So log base 9 of 27 is x. So that's the log form with this switched, or these two guys switched. And then in your calculator, if you do log base 9 of 27 using the using that change of base formula, so ln 27 over ln 9, you'll get the right answer, and it'll come out to be a nice answer. And if it's a nice answer, you know, like 1/2 or 1 or whatever, then probably that means you could have done it by comparing common bases and you just didn't notice. But there's nothing wrong with doing it like that. Okay, a couple of other things. We can go back and forth, doesn't matter which one we start with. So like in letter F, we have the x stuck in a logarithm instead of stuck in an exponent. And so we have the same strategy. First isolate the log part, because that's where the x is stuck. Keep in mind that you don't want to separate out this stuff, this log and its argument. This is the name of a function, so it's like having like f of x plus 3. and we really, we never, if we have a problem with a generic function and we say f of 2, we never separate the f from 2, right? This means something altogether. I mean, this is the name of the function and this is the input into it. This is not like a multiplication parentheses where you separate things. And so that's exactly what this is. It's just instead of f, the name of the function is this log with a little 2 next to it. So think of that as your f, and you won't be tempted to start manipulating through those parentheses. Anyway, so we want to change this to exponential form. This is a base 2 logarithm, and so it's going to be equivalent to a base 2 exponential. And so you can think of 2 to the blank equal blank, and the two blanks are going to get the inputs and outputs from the log, but they'll be reversed. So in this case, on the left side, 2 to the 5th is 32. So this is 32 equals x plus 3, and that's super easy to solve. So x is going to be 29. In G and H, the same things are going on. The reason those are there is to remind you that the buttons on your calculator are just shorthand for specific log bases. So don't forget that's really the log base E, and this is really the log base 10. You can just pencil a 10 in there. So if there's no base on there at all, that's referring to the button on your calculator. That's really base 10. So so once you realize that they really do have a base, you're following the same strategy. We would isolate first. I'll write this LOGE instead of LN, but I'm isolating that in the equation by subtracting 1 from both sides and then dividing both sides by 3. So I'll have log, I'll have log base E of x equals -4, switch to exponential form, e to the minus 4 equals x, and that's your answer, right? It says x equals. And of course, when you get an answer that's an exponent, that's easy to evaluate in your calculator. So finally, letter H, just for completeness, this already is isolated. There's nothing, the x is caught up inside of here. The log of this is already by itself. There's nothing else in the equation. And so I can just immediately switch to exponential form. So 10 to the whatever equals 5x minus 3. So whatever is 2. Right, the 2 and the 5x minus 3 are switching places when we go from log to exponential. And 10 squared is 100, of course. So so we'll have 100 equals 5x minus 3, and that's easy to solve, right? So yada yada yada. Okay, so that's the part of this worksheet that had to do with solving equations. The key step each time, well, there's two things, I guess. One is if both sides of the equation can be written as an exponential with the same base or as a logarithm of the same base, then it becomes easy. You can just say the inputs are equal. But if that doesn't happen, then the strategy is isolate the place where the x is caught by itself on one side, switch to the other form, and then solve the problem from there.